Fujimoto Masaki,
Yes.
Deputy Director General of ISAS, JAXA. What's ISAS?
It's a Space Science Institute of the Japanese Space Agency. So we run, planetary exploration missions or astrophysics missions.
But your life didn't start off as in space.
Yes, I was working on theory of plasma physics,
Right.
but around 15 years ago, I was asked to come to the institute, or maybe I was pulled to come to the institute,
Yes.
so that the institute can expand the international collaboration program.
And Japan has many programs in the past. It's always been involved in international collaboration. How important is international collaboration for JAXA?
Importance of international collaboration has been growing and growing, especially in these 10, 15 years. And now, into the future, we don't think our L-class programs, our large missions, cannot be performed without international collaboration. I can tell you an example, MMX, our mission to go to Martian moons, Phobos or Deimos,
Right.
and to do the sample return. There are something like 7 instruments on board, and 3 of them have the highest priority. But then out of 3, 2 will come from outside Japan, 1 from France and 1 from the US. And I think this is the model. This is what it will be like into the future.
1 from France and 1 from
US.
the US.
Yes.
Right. DLR is involved as well?
I'm sorry, I just happened 2 days ago. And now DLR and CNES agreed that they will collaborate to
Right.
provide a rover on the moon of Mars.
Right.
So that's, you can call it another instrument, and that's another key instrument. So
Right.
out of 4 key instruments, 3 will be from abroad.
Right, MMX is a future mission, moon exploration, and these are the moons of Mars.
Yes.
So we'll come back to the present and the past, but this is the future mission. What sort of timescale for launch are you looking at?
Yes,
for that?
MMX is planned to be launched in 2024. 1-year cruise to Mars,
Right.
3-year duration of stay around the moons, like Phobos or Deimos, most likely Phobos,
Right.
and then 1-year cruise back to Earth, and the samples will be returned in 2029.
And have you decided if it's Phobos or Deimos where the samples will come from?
Officially, I'm not supposed to tell,
Right.
but as a scientist, Phobos has been always a priority.
Right.
And as somebody supporting the engineering study, you cannot do engineering study without fixing your target.
Yes.
So we have been studying the mission, assuming that the target is Phobos, because getting to Phobos is tougher than getting to Deimos.
Right.
And as an engineering study, it's
Right.
natural that you take Phobos as the primary target for the study. I have to be careful here.
I'm always interested. These are all quite tough targets. They're very small moons, very far away, to actually get into orbit, land on them, bring a sample back. It's a huge challenge. But let me go back to Hayabusa 1,
Yes.
which is one of the very first missions. How long ago was that? It's about a decade ago?
Launched in 2003,
Right.
and sample return in 2010.
Right.
Yes.
And that was, I think the sample return, the quantity of the sample return wasn't as high as you anticipated.
True.
But all the other steps worked incredibly well, bearing in mind that you had to go out there, get into orbit, return, and you landed somewhere in Australia.
Yes, returned in Australia, yes.
And is there any highlights from the science that came back from the analysis of the samples returned?
Yes, the highlight is that, first of all, we went to the target asteroid Itokawa to find that it's a rubble pile. It's a assembly of rocks that must have been created out of impact event from. There must have been parent body that got into pieces.
Right.
And the reassembly of those rubbles made the asteroid Itokawa. But seeing the detailed look of a rubble pile object is the first time ever. So I think that should be regarded as one of the highlights, which people seems to forget, because there's an obsession that it's a sample return mission. We shouldn't talk too much about the remote sensing results, but I think that's not the right thing. So knowing it's a rubble pile, knowing that it was out of crash
Mm-hmm.
of objects,
Right.
then the obvious answer is that when did that happen? When did that crash happen?
Right.
But if you get the samples back, you can date the events. And now we know that the formation, the collisional process that created, that led to the formation of Itokawa happened about 1 billion years ago.
Right.
Yeah.
And it's quite interesting. So I remember the time when there wasn't any close-up images of asteroids. They were just tiny dots on
yes,
images on space telescopes. And the fact that it was rubble pile, that was not known. And it's up until then, people thought it was just a small body, maybe just a large boulder, a huge boulder.
True, yes.
But it was, and because it's a rubble pile, presumably you can see different structures and you can see the different constituents which would be on the surface rather than having to dig deep.
True. Yeah, and it gives you the idea, just gives you the idea about its origin and its history. If it's a monolith, then well, of course, you better understand its composition, of course.
Mm-hmm.
But if it's because it's a rubble pile and the target asteroid of Hayabusa 2, Ryugu, is also a rubble pile.
Yeah.
And out there out there for billions of years,
Yes.
the collision process must be going on. So I think rubble pile is it's something you should be interested in, and that the door into that science has been opened up by Hayabusa.
And it sounds almost negative to call it a rubble pile, but I remember the images of the Martian surface from Viking 1, 2 in the late 70s, and it looked like a rubble-strewn landscape. But the fact is, this is part of our solar system. We're actually there, and you actually bring bits of it back to Earth. It's almost like dreams come true. It's exciting.
Yeah, true. Like if you study about the formation theory of solar system or planetary system, you get to the idea that after all, collisional process is one of the key ingredients in the processes. Yeah. And then collisional process is something humanity don't really understand. If you make two things collide, what's the size distribution of the debris?
Right.
That's not an easy thing to answer. So I think we're all interested in the origin theme. But at the heart of the origin theme, we have this most difficult question about understanding the collisional process.
And by learning little bits of that kind of phenomena in asteroids, it'll help understand what happened when the Earth-Moon system were formed, because that also came out of a
giant impact. Yes.
We turn to Hayabusa 2, which has an incredibly successful week this week. We talk about the rovers in a moment, but Hayabusa 2 itself, it's the spacecraft, is entirely Japanese.
Yes, spacecraft itself, yes.
And then you had two rovers, the Minerva 1 and 2, and then you had the
Mascot. From Germany and France.
So Minerva 1 and 2, they're Japanese?
Yeah, I usually call it Minerva 2-1 and Minerva 2-2, by the way. But,
thank you.
Yes, one is from us, JAXA, and the other one is from the University Consortium. And then the German-French rover by the name Mascot.
So, in terms of size, the Minerva rovers were quite a bit smaller.
It's really tiny. Yes,
right.
Yes.
And they were on the surface of Ryugu earlier this week. I don't know.
No, about 2 weeks ago.
2 weeks ago.
Yes.
And what kind of science? I take it they also didn't have any solar panels or the duration.
It's like this size. The surface is covered by solar cells, so it has a rechargeable battery.
Right.
On the other hand, the German-French rover didn't have the rechargeable battery. That's why it was dead in 17 hours.
Right.
But Minerva 2-1, it's still surviving.
Still surviving?
Yes.
Still sending data?
Which is a pleasant surprise.
Really?
Yeah. and besides, it's important to have them survive for a long time, because when we got to Ryugu, we find its face to be unfriendly. We assume that there should be a smooth surface from which sampling is easy. Touchdown and sampling is easy. But when we got there, we realized that, everywhere is rough. It's not easy to land. But we managed to define the landing site candidate for the sampling. But still we need more information. We still need to learn how to improve our accuracy of navigation, and we still have to have a better feeling about what it is like to be touching down on that surface. So having a robot on the surface, Minerva and Mascot, and giving us the close-up image of the surface. It's science-wise important, of course, but it's not only science. It's not additional science to the main spacecraft. It's helping the main spacecraft to have a detailed, safe scenario for touchdown and sampling. So it's really a critical element of the mission.
And how did you get the rovers, Minerva and Mascot, onto the surface? Was it just a question of when they were released by Hayabusa 2?
Yes,
or did they have some propulsion on board on their way to the surface?
No, they don't have anything. They're just free form.
Yeah.
But the main spacecraft takes them to something like 50, 60 meters above the surface, and that's where they are dropped, from which they are dropped. But then the terminal velocity on the surface is like 10 centimeters per second. So it's really soft.
Yeah.
And they manage, and even if the surface is rough, they manage to survive and bringing us some incredible data.
And one of the things that almost goes over my head is this idea that you've got Hayabusa 2 to within 60 meters of an asteroid.
True.
That's incredibly close, bearing in mind that you're operating this spacecraft from Earth. It's very scary. You could easily, if you get some of the maths wrong, then Hayabusa would actually make a collision with the asteroid, wouldn't it?
That's a good, interesting question, because we have to touch and go anyway. So.
Oh, of course, yeah. So, okay. So you've got two mini. Let's just talk about this term rover. These aren't actually rovers because of this very tiny escape velocity. They don't actually have wheels. Do they?
True. So they hop. There's an internal mechanism that you have an arm moving, and then the body itself moves around.
Right. It's a bit like shifting the weight.
True.
And then it moves along.
Yes. And when the Minerva hops, it hops for 19 minutes, and then come down. So it's
19 minutes.
Yeah, we call it hop. But it's almost like a flight because of the microgravity. Yeah.
And how high? What sort of altitude would it get?
I cannot give you. I forgot the number, but you can imagine. I think 19 minutes is more.
Yeah. Amazing. Mascot has been remarkably successful. Seen some pictures from there.
Yeah.
And that was a French-German contribution.
German-French.
German.
Be careful.
Oh, is it?
German-French.
Right, okay. How big was that? It was quite small as well, 10
yeah, it's like this size,
right.
And 11 kilogram-ish.
Right.
Yeah.
And the instruments it had on board were a camera, a radiometer.
Yes, magnetometer, and then the spectrometer, which will tell us the composition of this weird surface.
Right.
The surface is super dark. It's darker than any meteorites we have on Earth. So which means that any sample we bring back must be new. But before getting the sample, spectrometer on the surface should be telling us what that weird material is like.
Right.
Yeah.
And it was only didn't have any solar panels, so it operated for about 17 hours, and now it's stopped to work. Yeah.
Yeah. So I had a chat with the project manager of Mascot, and of course she shed her tears, of course.
Right.
And 70 hours. Yeah, it's not easy to judge. You can easily argue that why didn't you have the solar cell, why didn't you have the rechargeable battery? But the answer from DLR is that cost and the schedule, of course.
Yeah.
But
we can always complain, but it's incredibly successful.
True, I think so. Yes.
It's the bottom line. I know you have limited time, so I'm going to just ask a couple more things. You've got another mission to the moon, the Earth's moon, planned, Selene R.
Yes.
What can you tell us about that?
Yes, Selene R is a mission that's being planned. It will land on the polar region of the moon, and then there's a lander and then the rover, and then the rover will run around and then dig into the subsurface, get some samples, and then bake it, and then see what comes out of the samples. So it's a mission to detect and analyze the volatiles in the subsurface of the moon. So water ice is obviously one of the targets.
Right. So when you say bake it, the purpose is to do a chemical analysis of the contents.
It's like a gas chromatography. That's the word. at different temperatures, different materials, depending on its volatility, comes out. And that's what we analyze using the mass spectrometer.
And what collaboration is involved in that mission?
Yes, it's a collaboration with India. We will provide the launcher and the rover, and ISRO will provide the lander. That's the basic plan as of now, and it's ongoing.
Right. And what sort of time scale?
Early 2020s. Yeah.
And on top of all that, what else are you planning in JAXA in terms of space activities generally, and solar system exploration in particular?
Yes. So we had Hayabusa 2, and we will have MMX. For us, MMX is another asteroid mission. And we are interested in small bodies born in the outer part of the solar system, because they contain volatiles, they contain water in them, and it must have been some of them, a class of them that brought water to Earth, which must have been born super dry. Earth was born in the inner part of the solar system, so its original shape must have been super dry. So somebody has to bring water to make us be here today. And so I think it's nice to have a series of explorations to the small bodies, different small bodies, but born in the outer part of the solar system. Hayabusa 2 is the first one. Going to Mars and Moon is the second one. Then we have a plan to go to Trojan asteroid of Jupiter.
Right.
So that's yet another small bodies in the outer part of the solar system. We have a plan to participate in NASA's mission, which is not selected yet, but it's in its final stage of selection. It's a final candidate for selection, and that will bring samples back from a comet.
Right.
So a comet is another small body in the outer part of the solar system. So we have a strategic plan to explore the small bodies in the outer part of the solar system.
India announced its human spaceflight program. JAXA have any intentions of going that far?
Yes, now we have the human exploration program by participating to international space stations.
Right.
Now that human exploration people are thinking about converting their program into the space exploration, exploration of the Moon and Mars. And in the new shape that we will be having, I think more collaboration, more communication between science and human exploration will be necessary for sure. And I think we at the Science Institute are happy to have discussion with them, and we are having discussion with them. And I think things will be in good shape in next 5-10 years. And MMX is already one of the collaboration items.
Well, Deputy Director Fujimoto Masaki, that's been fascinating, and it's great to hear that the work that you're doing out in these asteroids are really connected to us, because they, as you say, brought water to the planet Earth, and without that we wouldn't be here. Thank you very much indeed.
Thank you.